Welcome to another Great Cow BASIC tutorial. This is part 15 for the PIC18FxQ41 chipset. Where are we? We are on number 16, which is using memory, the PROGMEM and SAF memory within the microcontroller. Exciting stuff. I'm using a microchip low pin count demo board. We will have a quick look in the lab, but this is the one I'm using. It's that's the last time you'll see it. I've got the serial connected as in the previous tutorials with ground and zero, and that's about all we're going to see today of that. There's just no point in looking at it because we're going to print everything out on the terminal. This is the layout so that you can copy it. As I've just said, I have got the terminal to transmit connected to this pin here, third pin on the bottom on the right. There we go. The TX goes there, and the ground is connected into here. Okay, here we go. Very simple. Thank you, Chris, for the layout. So let's have a look at the memory itself, and we'll do a memory overview, and then we'll dig a bit deeper. Okay. So the memory has three different types according to the datasheet. We have PROGMEM, data RAM, and data EEProm. I'm going to be focusing on PROGMEM today, and just prove to you that there's two different characteristics inside of there. And we're not going to talk about data RAM at all, the second one, because that's volatile. If you use that for variables, and when you turn the microcontroller off, they disappear. And we've looked at EEProm in a different tutorial, so consider that as a peripheral, and you'll be fine. That's the way to think of it. And that's in the data sheet. That's not me talking. That's in the data sheet. So let's have a look at that in a bit deeper in terms of PROGMEM. Well, PROGMEM in a datasheet comes in many different sort of flavors, but it essentially comes to the major block of 32 kilowords in this particular chip up here in the top right hand corner, and other smaller areas of configuration and data to operate the chip. And what we're going to do is focusing on the PROGMEM flash area of the memory to insert some data. Okay, we're going to use the self-write capabilities of this chip to save some data. Well, if you actually look at the data sheet very carefully, you will see in this area here, open brackets 1, close brackets. And that area is 128 words of SAF, or storage area flash. And that has different characteristics in terms of the number of writes and its storage. So you've got EEProm for long-term storage, and you've also got SAF. And we treat those very differently because of the way that they operate. If we then look at data EEProm, as I've said, there are a different set of operations, EP write and EP read, and it just works. Okay. All right. So let's have a look at using the PROGMEM. Why would you use it? Well, you've got your program. It's in this blue area. Our compiler puts it from the memory area 0 here, and it then populates it upwards in the program. And then if I wanted to put some reference data in there, I would write it to the top of memory here. I'd write it right at the top, well away from anything else, to ensure that my program didn't encroach. However, if you're using something like MPLAB, then you're going to have to do it slightly differently, because MPLAB puts what's called a little vector in here at 0, and then your program jumps out to the top end of memory. So your reference data better go at the bottom end of memory, just above this vector. Otherwise, you're going to overwrite your program. So if I wrote my program into here, put my reference data in here, my program will stop working. And the same down here, if you put reference data in the blue area, it will stop working. Be careful with the self-write facilities. Why would you want to do this though? This is because you might want to put a GIF in memory rather than putting EEProm, because they're quite small. You want to put something like a picture, put it in there. It's fine for that, but just be careful where you put it. We use what's called direct PFM, that's program memory. We use 0 to the top end of memory, okay? And that might be FFF0, whatever your chip is, okay? We just start at 0 and work our way through. So you have to be very explicit about where you land it. Let's look at SAF. Slightly different. We know it's 128 kilowords, 128 words at the top of memory. We know that from the data sheet. So it's always here. It's always at the bottom here in this little diagram. And you need to make sure that you don't overwrite it, because again, if your program is sitting there like in MP Lab, then you need to make sure that you create headroom for it inside of your program so that your program doesn't overwrite your SAF area, and your SAF data doesn't overwrite your program. They mustn't encroach. So we use what's called offset addressing for SAF. This is 0, this is 127, and that's as simple as that. You just say to it, SAF, the write operation 0, we'll put it at location 0, etc. Very simple, keep it nice and easy. So let's walk the examples. We'll look at program first, and then we'll look at SAF. Just toggling out to my, there we go. So if we look at the program, we've got the standard chip and the option explicit, very standard, PPS to set up the serial. We've done that many times, and then the two constants to set up the serial output. And after that, we can use the hser hardware serial commands like print, carriage return, line feed, etc. So what we're going to look at to start with is PFM program memory read. I'm going to read words, put them on a terminal to understand what's going on. And essentially all I'm doing is looping through using a variable as an address pointer from 0 to 1F, which is the first 32 bytes or 16 words. And I'm going to put them on the screen using a function called PFM read word with that address as a parameter. It will return it and put it inside data word, and I put data word on the screen. Let's see it working. Once we've seen that working, then we're going to use the write function. Switching out to another view, I've got a terminal now on the left and a PIC kit on the right. And we can see that we've got some action. What I'm going to do is just erase that, kill the power, and just do it again for us, okay? So that we can see it all happen in slow time. Here we go. There we go, excellent. Now, on the screen here, I've got the address 00 through to 1E. That's the first bank. This is the set that I've asked for, and I've got some values: E06, F000, FFFF, 4 Fs, and then 10 hex. Well, let me just read that in from using PIC18FxxQ41, and you will see that that's exactly the same as what's in memory. So I've shown you very quickly that you can read in program memory, and you could do that to any address with reference data. So on the screen here, we've got EF06, and in memory here, EF06. Next, F000, and we've got exactly the same sequence right the way through to the end, 6E0D. So we can use this really simple method called PFM read word to read words, and we can do that throughout the whole of memory, because I just did it from 00 to that small segment there. So let's have a look at using PFM write. All I'm going to do is I'm going to write a number 55 and the hex 1234 out to these two memories respectively, F0 and the top end of memory, which is FFFE. And then I'm just going to display them using exactly the same function as I used before, which is read the word and put that word onto the screen. Then we compile that up and we'll see what happens. We'll zoom in on the terminal and we'll see it says that at memory location FFF0 there's a value of 55. But how do I know that? Well, I can use my PIC18FxxQ41 software. You could use IPE. You could use others. Just extract it and look at it. But this is just quicker. I'm going to cursor to the end of memory. And look, I've got 55 exactly where I would expect to see it. And 1, 2, 3, 4 at the top end of memory. So I've written out, because it wasn't in my program. I guarantee you it wasn't in the program. If I import that program, it's not there. but the moment it operates, the moment it runs, and it's got some power on that thing, it will then update these 2 bytes to 1 byte and 1 word, because that's what's in my program. So I could load in a whole GIF if I wanted to. Excellent. Very simple. Direct addressing, and the addresses there were explicitly passed into the function called PFM read word. Let's have a look at SAF. So SAF is special area memory, and if I push this button here, it turns yellow. This area of memory turns yellow, and it says here that this is the SAF area because it's yellow. If I erase the part, just to prove it to you, in actual fact, I can show you other tricks, but we won't today. I've got time. It's actually restored back the SAF because it knows what it's doing. So SAF starts at the memory address of FF00, but I don't need to know that in my program because my SAF code handles that for me. So let's have a look at how we do that. So I'm just going to put an end in there. Top of the program here, the demonstration is exactly the same. Set up the chip, set up the serial, and then I'm just going to, I'll go out to the SAF program even. What I'm going to do is I'm actually going to put a series of bytes into an array, send that array direct to the SAF. Okay, so I just use a function called write a block. So I can write a block which is to address 0, send my buffer of 8 bytes, and there's my number 8. So 0, an array name, and then the number of bytes I want to send through. And it will put it directly into SAF in that particular area, so you don't have to know the SAF memory. That's what comes with fiddling with code, right? I did change the code. I'll just get rid of that. Now I'm going to go out to the zoom, and we'll see it zoom in, and we'll see that the display will change. Very different. So what we're doing now is we've written out an array of 8 bytes. I'm just going to clear the terminal now, and then just turn the power back on so we can see it. And I wrote out to it the values of 20, 2C, 58, 5B. If you can remember those, that's really good, because I'm going to read that now inside of PIC18F Plus, and when I read it back in, we will see them appear exactly here. So what we see on the terminal is what we see in PIC18F Plus, and we're using write block as an array. Now exactly what we expect to see. Let's go back to our code though. We can write bytes if we wish. In this demonstration, I have a little end there just to stop it from running right the way through. You can just put some words into variables, and then you can just write them out using what's called SAF write word. And I'm going to put those at address 0, 10, 12, and 14, so they'll be consecutive. And they'll write those out into this area of memory, into these 4 words. So we're just going to let it complete. Let me zoom in onto that. It will write them into these 4 words here. So in the terminal, I can see it's written them out. If you look on the terminal display, it's written them out into here. But how do you know it's actually done it? We can read it in just to check things out. And we'd expect to see them sitting here. So I've used write a block through an array and write out single words. It's very simple. You could write out a byte if you wanted to. There we go, exactly what we see and what we expect. So, very simple to use writing into ProgMem. You can just grow that out now into your own program that is much larger and more functional and richer in terms of the capabilities. You can take that, suck in a GIF file, write it out into ProgMem, write out reference data into SAF using the different codes that interoperate correctly, and you shouldn't have any issues using the vast amount of memory you've got available to you in the 18FxxQ41. So what I wanted to show you was how to write data out. I think I've done that, and how to write it into PFM and into SAF. I think we've done that. So tomorrow we'll be looking at the toolchain itself, just a high-level introduction, tells you what's going on in the background, and we'll follow it up with assemblers and alternatives. So enjoy.